This code imports Python libraries commonly used for mathematical and scientific calculations, data analysis, visualization, and deep learning. Each library has a specific purpose to fulfill these tasks effectively.
The ***math** module provides functions for common mathematical operations, such as square roots and logarithms.
NumPy** is a key tool for scientific computing in Python. It allows users to work with extensive multidimensional arrays and matrices, as well as provides essential mathematical functions that can be performed on these arrays. Pandas is a library in Python that offers added features to help with analyzing and working with data, particularly when it is structured in tables. Matplotlib is a Python library that enables users to create various types of visualizations, such as static, animated, and interactive plots. In the context of market data, Matplotlib is commonly utilized for plotting data and adjusting date formats on the plots.
TensorFlow is a library used for deep learning.
It helps in creating and training neural networks. Sclearn is a set of tools that are used for machine learning and statistical modeling. It includes various metrics that help in evaluating the performance of models. Seaborn is a data visualization library built on top of Matplotlib. It offers a simple way to generate visually appealing and informative statistical graphics. Plotly is a tool for creating interactive visualizations like plots, charts, and graphs, with various interactive features. This code prepares the software environment for conducting data analysis, visualization, and deep learning tasks by importing the required libraries and modules. This code converts a CSV file into a pandas DataFrame. It converts the date column to a datetime format and makes it the index. Then the code removes the date column and returns the updated DataFrame. You will be using the nable_large.csv file, which is stored in the data folder. In Python, the variable name df is commonly used to refer to a DataFrame object, especially within libraries like pandas. A DataFrame is a structured way to store data in rows and columns, often used for data analysis and manipulation. The df variable holds this data and can be modified, analyzed, and displayed visually for further insights.
This code creates a function named plot_data that takes a DataFrame as its input.
The function makes a copy of the DataFrame and calculates the number of rows and columns needed for the plot based on the DataFrame's shape. It then uses Matplotlib to generate a subplot figure with the defined number of rows and columns.
The function generates a line plot for each subplot using Seaborn's lineplot function, with the data from the respective column of the DataFrame.
It further adjusts the x-axis ticks by rotating them, resizing labels, and setting the major tick locator.
The function organizes the subplots neatly by using tight_layout, and then shows the plot using Matplotlib's show function.
Before running this code, make sure you have imported the required libraries like pandas, Matplotlib, Seaborn, and Matplotlib dates. The code introduces a function named createFeatures that enhances a DataFrame by calculating and appending new columns features based on existing data. This code summary explains the functionality of the code. To calculate the daily closing price difference, a new column called close_diff is added. Moving averages or MAS are calculated for several time periods: 200-day, 100-day, 50-day, 26-day, 20-day, and 12-day, and then added as new columns to the data. This function determines the variances between different moving averages and the closing price. It then includes these variances as additional columns in the data. This action computes the smallest and largest values for both low and high prices across various timeframes, and then includes these values as new columns in the data. To determine the volatility of the closing price over a 20-day period, the standard deviation is calculated. This value is then added to the data table as a new column.
The tool computes exponential moving averages (EMA) for various time periods and includes them as additional columns.
Two new columns are added by shifting the closing price by 1 and 2 days, creating lagged versions of the data. The upper and lower Bollinger Bands are determined by using the 20-day moving average and standard deviation. The K-ratio and relative strength index are indexed to the lowest and highest prices observed over a 14-day period.
The moving average convergence divergence (MACD) is a technical indicator that is calculated by subtracting the 26-day exponential moving average (EMA) from the 12-day EMA. This action involves replacing any empty cells in the dataset with the most recent closing price available.
The function ultimately returns the data frame with the new features included.
This code uses a function called createFeatures to modify a data frame named df by adding new columns.
The function takes df as input, and after it runs, the updated data frame with the new columns is printed out. This code creates a function named filter_data, which operates on a data frame. It begins by sorting the input data frame based on the date column, making a copy of the sorted data frame. It then defines a list of features called features and prints this list. Next, it converts the sorted data frame into a new pandas data frame named data. Finally, it filters the data frame to include only the columns listed in the features list and returns this filtered data frame. To successfully run the code, make sure to import the pandas library at the start of your script. This code computes the correlation coefficient between the close column and all other columns in the data_filtered dataset. The correlation coefficient shows how the closed column is related to each of the other columns, with a value that can range from -1 to 1. A value close to 1 indicates a strong positive relationship between the variables. When the value is close to -1, it indicates a strong negative relationship between the variables. When a value is close to 0, it indicates that there is either no relationship or a very weak relationship between the variables being studied.
This code helps determine the degree of correlation between the closed column and the other columns in the dataset.
Understanding this relationship is crucial for predictions and data analysis. The code creates a function named train_test_split that uses a data frame as its argument. The function divides the data frame into a training set and a testing set. It does this by selecting a sequence length and splitting the data based on a 70:30 ratio, where 70% is allocated to the training set and 30% to the testing set. The variable sequence_length is assigned a value of 100, indicating that every sequence will have a length of 100. The code calculates the index to split the input data frame by using the formula math. Len df 0.7. This index marks the location where 70% of the data will be used for training and the remaining 30% for testing.
It assigns the rows from the beginning up to the split index to the training data frame called _train_df. The code assigns rows in a data frame, starting from a specific index minus a given sequence length, and ending at the last row, to a new data frame called test_df.
At the end, it provides back the training dataset, testing dataset, and the split index. This code function divides a dataset into two sets, a training set and a testing set. The training set consists of the first 70% of the data, while the testing set contains the remaining 30% of the data plus some rows from the past based on a specified sequence length. This code divides a dataset into two parts for training and testing, using the train_test_split function. The training data is stored in the train_data variable, the testing data in test_data, and the ratio of the split in the split variable.
Lastly, it shows the contents of the test_data variable.
The code creates a function named preprocess_data, which normalizes the input data using MinMaxScaler. This code performs the following actions: receives input data. This step involves changing the structure or format of the input data. Displays the structure of the resized data. MinMaxScaler is utilized to rescale the data. The function returns both the scaled data and the scaling method used. The code pre-processes two sets of data, train_data and test_data, by applying a function. It then stores the scaled data and scaler in variables train_data_scaled, test_data_scaled, and scaler for future use.
The code contains a function named partition_dataset, which requires two parameters to be passed: sequence_length and data.
This is the reason for something to exist or be done.
This function is meant to split a dataset into input sequences X and their corresponding output sequences Y for training a machine learning model.
The input data is typically represented as a 2D array or matrix, where each row in the array stands for a different data point. The sequence_length parameter determines the number of data points grouped together to create an input sequence.
An explanation is a detailed description or clarification of a concept, idea, or process to help someone understand it better.
It breaks down complex information into simpler terms. The function begins by creating two empty lists X and Y. These lists will be used to store the input and output sequences respectively. Next, the program determines the size of the data provided by the user. It goes through the data starting from a specific index sequence_length all the way to the end of the data. During each iteration, a section of the data with a specific length called sequence_length is taken out and added to the X list. The next data point after the subsequence is extracted and added to the Y list. This value is used as the prediction for that input sequence.
Lastly, it changes the lists X and Y into NumPy arrays, then gives them back. This function organizes a dataset into groups of input sequences X and their corresponding output sequences Y.
It is typically used to train a machine learning model. This code snippet appears to be used for a task involving machine learning or time series analysis.
It is likely preparing the data for model training and testing.
It does so by dividing the dataset into sequences of a predetermined length. Here is an explanation of the code's functionality. A variable named sequence_length is assigned a value of 100. The next step involves splitting the scaled training data train_data_scaled into input sequences and their corresponding output sequences using the partition_dataset function. The input sequences are saved in X_train, and the output sequences are saved in Y_train. The partitioning process is repeated for the test data test_data_scaled. The input sequences are stored in X_test, while the output sequences are stored in Y_test.
Lastly, the program will display the dimensions of the training and testing input sequences X_train, shape, X_test, shape, and output sequences Y_test, shape.
The output sequences of the test data's Y_test are also displayed. The code is organizing training and testing data into input and output sequences of a specified length to prepare them for a model. It then provides information about the shapes and contents of these sequences. This code snippet prints the last element of the list x_train at index 1 and position sequence_length -1 as well as the last element of the list y_train at index 0.
The code initially assigns the variables the value equal to the number of columns present in the _test array.
A sequential neural network model is built using the Keras library. The model is made up of 2 LSTM layers with 128 and 64 units each. The first LSTM layer takes input in the shape determined by the rows and columns of the x_train data. It uses ReLU activation function and outputs sequences of data. To prevent overfitting, a dropout layer is added after the first LSTM layer. This layer randomly deactivates a portion of input units by setting them to 0 during training updates. The next layer in the sequence is another long short-term memory LSTM layer with 64 units and no return sequences.
This layer is then followed by a dropout layer. To finish the process, a dense layer is included in the model.
The number of output nodes in this layer aligns with the size of the output data as represented by the out variable. The Atom optimizer is set with a learning rate of 0.001. The model is compiled to use Atom optimizer and mean squared error as the loss function for training the neural network.
The model summary function gives a concise overview of a neural network model.
It displays the model's architecture, such as layers, shapes, parameter count, and whether the layers are adjustable. This summary is useful for grasping the model's structure and elements efficiently.
This code demonstrates how to train a machine learning model using TensorFlow, Keras.
The code initializes an early stopping callback, which halts the training if the validation loss does not improve after 5 epochs. To train the model, you can use the model.fit method, providing it with the training data x_train and y_train.
Additionally, you can include validation data x_test and y_test.
In this case, the training is set to run for 100 epochs, each with a batch size of 32. An early stopping callback is added to monitor the training process. Once the training of the model is finished, it is saved as an HDF5 file named my_model th5 by applying the tf Keras models save_model function with defined parameters. This code generates a plot that visualizes the training and validation loss of a machine learning model as it trains. It uses the matplotlib library to create a figure of a specific size, and then sets up a subplot with 2 columns. The code creates a plot using training loss and validation loss values saved in the history object.
The plot is customized with labels, a legend, axes, labels, a title, and adjusts the y-axis limits based on the maximum loss value in the data.
The plot is shown on the screen, allowing users to see how the loss values change throughout the training epochs.
This code uses an existing machine learning model, which has been trained beforehand and saved in a variable named model.
It predicts output values by utilizing input data provided as x_test. The predicted values are then saved in a variable called test_predict. These predictions can be further examined or used to evaluate how well the model is performing. This code reverses the scaling of predicted values and true values to their original unscaled format, using the scalar inverse_transform method. The function then returns the number of elements in the predicted values array test_predict. This code computes and displays various error metrics used to assess the effectiveness of a predictive model. RMSE stands for root mean square error, which is calculated by using the mean_squared_error function from the math library.
RMSE helps us understand the average difference between the actual and predicted values in a model.
Lower RMSE values suggest that the model performs better. The mean absolute error MAPE is computed with the mean_absolute_error function to measure the average absolute difference between actual and predicted values. Lower MAPE values indicate better performance.
The mean absolute percentage error MAPE is a measure that calculates the percentage difference between the actual and predicted values.
It provides a relative error percentage compared to the actual values, with lower MAPE values indicating higher accuracy.
The median absolute percentage error.
It is calculated as a percentage, similar to mean absolute percentage error MAPE, but it uses the median instead of the mean. MDAPE is a more robust measure because it is less affected by outliers in the data.
After performing calculations, the values for RMSE, MAPE, and MDAPE are displayed with 2 decimal places for better clarity.
These metrics provide insight into the accuracy of the model's predictions in comparison to the real values. This code divides a dataset into 2 parts, training and validation, based on the values stored in the variable split.
The train part includes data from the beginning to a certain point of separation, while the valid part includes data from the separation point to the end of the dataset.
The code creates a new column named predictions in the valid dataset.
This column is filled with values retrieved from the variable test_predict_out_window.
These values likely represent the predictions generated by a model when applied to the validation dataset. This code creates a visual representation of how well a model can predict stock prices. It produces a plot that includes the following components.
The figure is 16 units wide and 8 units high. The plot is titled Model.
The x-axis is labeled as date and the y-axis is labeled as close. It shows the real closing prices of the training data by connecting them with a line. It shows the real closing prices of the validation data, valid close, by using a line on the plot.
It shows the expected closing prices on the validation data by using a line graph for valid predictions. A legend in a plot is used to identify the lines as either train, validation, or predictions.
The plot displays the closing prices of the stock data, both actual and predicted.
This code generates a 16 by 8 inch graph. It plots 2 lines, one for the actual close prices from test data and another for the predicted close prices.
The x-axis is date and the y-axis is close price. It visualizes how closely the model's predictions align with the actual data.